Well, good afternoon to all the participants who have joined the 78th course through the distance learning program of IIRS. I welcome all of you to this special course organized on geospatial technology for archaeological and cultural heritage studies. Earlier, we had planned this course for about 2 weeks and had planned to conduct very detailed lectures and also some demonstrations related to archaeological studies and cultural heritage studies, monitoring and management documentation of heritage, built heritage especially, through geospatial technology. However, due to the prevailing situation that we have at our end and all over the country and the world related to the pandemic, all of us are facing a very difficult situation. And due to that, we had to compress the course to 1 week. We shall try our best to convey all the technology, the methods, and the case examples in this 1 week in a compressed format. I welcome you all once again. I am happy to announce that we have about 9,000 participants from about more than 850 plus institutes that have been able to join us. I hope you have a very fruitful learning experience in this 1 week. With this, I will begin the first lecture, which is the introductory lecture on geospatial technology for cultural heritage use and archaeological studies. We will have an overview of the technologies that are available. Also, I will take you through the basics of all the technologies, what their advantages are, how they help us to go about mapping, monitoring, documenting heritage structures, and how it helps us in archaeological studies. And then I will take you through the case examples of each of them, some of them from the international and national researchers, and some of them are the studies that have been done at IIRS. So with this, I will start the lecture. So as I said, I'll tell you about heritage, what heritage is and its importance, the Earth observation and geospatial techniques that are available to us in the current scenario, how these techniques and methods are useful for archaeological applications. Together with their advantages, we will also highlight the limitations and how we can use an integrated approach. You can club different technologies, different data from different sensors, and also club different types of image processing and GIS techniques to come up with a very comprehensive documentation plan and also a plan for mapping, monitoring, and management of these heritage sites. In the current course that we have planned, we will only be taking you through methods and techniques for cultural heritage. There are also the same technology can also be used for natural heritage. However, right now we are not highlighting any examples of the natural heritage studies, right? And so, as we can say that heritage can be seen as a bridge or arch between what we inherit from our ancestors through time and what it is that we will leave behind for the future generations. So it is an arch or a bridge, and a very important bridge that we pass on from generation to generation. The importance of the cultural and natural heritage documentation is very well recognized at the international level, and there is an increasing pressure on all the scientific community and the archaeological scientists and the historians to document and preserve heritage as well as possible, and currently to use the digital methods available to us. The precise documentation of cultural heritage status is now essential for its protection and scientific studies, that are carried out during the restoration and the renovation processes. Now, to summarize, the heritage types of heritage could be basically classified into cultural property, or something which is physical or tangible cultural heritage, like monuments, temples, forts, all these kind of built heritage structures, or even written manuscripts that you have, paintings and so on. So these would be property, something which is physical and can be seen and held. The next category would be intangible culture. So these are non-physical aspects of the culture or heritage. For example, it could be folklore, folk dances, songs, so on and so forth, some customs that are passed on, and so on and so forth. So these are non-physical aspects, so intangible cultural heritage. This also forms a very important part of the heritage that that is the term that is heritage or culture. Then comes natural heritage, which refers to biodiversity that is available. So like the Valley of Flowers in Uttarakhand. So it's a biodiversity heritage, or geobiodiversity, like the Yellowstone National Park in the United States, and several other, the Uluru Rock in Australia, and so on and so forth. There are several such natural heritage, the root bridges in the Northeast. So there are several such examples of natural heritage, which geospatial technology can play a very important role in documentation and management and monitoring of such natural heritage features as well. Currently, as I said, in this 1 week program, we will only be focusing on the first type, that is the physical or built heritage, to be very precise. We are going to be taking up heritage sites as monuments, etc., and how to document them, manage them, and monitor them, how to assess damage that may have happened, and then for reconstruction, etc., what steps may be taken for protection of the monuments, how we can use Earth observation data, how we can club satellite data, that observation data, with, say, aerial data or UAV data, augment that with ground-based data collection, like from terrestrial laser scanner or ground-based photographs. These days, even crowdsourced data forms a very, very important part of data collection process, and we get very valuable information from the crowdsourced data. Heritage structures, heritage monuments, etc., can be reconstructed using data from crowdsourced examples. Similarly, there are, say, several kinds of remotely sensed data, like laser data, microwave data, and so on and so forth. So we can club I will show you examples, and also in the forthcoming lectures, you will see examples that will help you to see how this integrated approach gives us a very detailed set of parameters to document the cultural heritage. So the rapid advancement in new technologies has, made available this practice of recording heritage sites and monuments, and it has made it easier. Digital tools and media also offer new or sophisticated means for the user to be able to collect, analyze, and disseminate this information about heritage sites. When I say heritage sites, I am specifically referring to built heritage structures. New technologies and a growing need to document and preserve information and objects related to cultural heritage is also expanding at a very rapid rate. So people have realized that these advanced technologies can help us and augment our process of documentation and the preservation that can be used for reconstruction later. So 3D recording, we can also collect information not just in 2 dimensions, but as we will discuss later, by using means of photogrammetric data collection, we can do a 3-dimensional recording. Consequently, documentation and management of the cultural heritage, and this provides the necessary details and information for constructing heritage inventories, These inventories can be used for assessing damage, risk management, and the overall management and monitoring of the heritage assets. Now, Earth observation, we will begin with Earth observation from the satellite platform and how we can use geospatial techniques like image processing, methods of GIS, deep learning, and so on and so forth to extract maximum information about the heritage structures and put them in a virtual heritage management system. So Earth observation, as you know, can be applied to the study of cultural and natural heritage and also archaeological studies. This would include documentation, site management and monitoring, damage detection, change detection. So if I have satellite data for a considerable period of time, say from the 1970s till date, I can see how the area around the heritage structure has changed, what anthropological aspects have affected it, how it has changed over time, and what are its imprints on the landscape. So these things can be studied. Also, we can study not just the features or manifestations that we see on the surface, but with techniques like microwave data or ground penetrating radar, we can also have an idea or have information about the subsurface features. So buried information for possible excavation, etc., or ancient buried cities or sites or artifacts, etc., can be excavated with the help of such techniques. In this week, we have also tried to incorporate the basics of such technology for you. Now, this technique provides extremely useful information for researchers, decision makers, and planners, and also for the very common man like you and me, so that we are able to see and appreciate and visualize this heritage. It becomes especially important in times such as these that we are going through, where going out to a museum or to a site becomes very, very difficult. Such techniques will help us to make virtual museums, and people can make use of those. Researchers can make use of such facilities and study and appreciate the heritage aspects that we have through such means. So Earth observation, as we know, encompasses different types of sensors, which could include microwave sensors or laser sensors, could be optical sensors operating in the optical wavelength. These could be multispectral sensors, that is, sensors which give us data in multiple regions of the electromagnetic spectrum. They could also be hyperspectral sensors, that is, which very high spectral resolution, narrow wavelength, and especially useful for studying features which can be deciphered only in a very small, narrow, contiguous band. We could have varying platforms as well. For example, we could get data through satellite-based platforms, aerial data, aerial photographs, or UAVs, unmanned aerial vehicles. With these, we could do either two-dimensional studies, or if we are applying using techniques like SAR or LIDAR or photogrammetry, then we could also generate three-dimensional views and club them with other ancillary data like the image, interpreted data, classified data, and so on, and come up with a comprehensive documentation of the entire heritage site. It could also be augmented. Information extraction is augmented and aided by use of image processing methods, and then it can be incorporated into an information system like the GIS. So we could call it a heritage information system. Now, these kind of intelligent systems will enable monitoring and modeling of heritage structures over different regions at different scales, and in which ground observations may not be possible due to physical or political constraints. So, as I said, in any such situation where we are actually not able to go physically due to any constraint like regions like Syria or war-torn Afghanistan and so on and so forth, where people are not able to go, but there are considerable heritage structures. So Earth observation data from a space-based platform helps us to get an idea and do mapping and to monitor such heritage sites without actually having to, or to with minimum groundwork. Such structures can be monitored, modeled, and monitored. The other big advantage of Earth observation data is that it provides high spatial, temporal, and spectral resolution data. So I can get very high spatial resolution data, which will help me to see the features at different levels of detail. I also get temporally varying data, that is at different time periods, so that we are able to monitor it at different times, and do a change detection kind of study. Spectral resolution, as I said, especially with hyperspectral data, if there is a feature which is present only in a very narrow region of the spectrum, then we will be able to use this high spectral resolution data and interpret those kind of or similarly reflecting features. One will be able to make a very detailed mapping of that area. Stereo mapping or three-dimensional mapping is also possible with photogrammetric processing. And sensors like the SAR or microwave sensors are all-weather imaging, have all-weather capabilities. We can do day and night imaging. Since they are active sensors, they also have penetrating capabilities. So cloud, etc., will not matter, smoke, fog, etc., will not matter so much. And these give us an all-round ability to be able to club and complement information from all of these sources together and come up with a very comprehensive and detailed methodology to map and monitor these heritage sites. Also, improved satellite and sensor technologies with increased frequency of satellite measurements, that is increased temporal resolution, and easier access. These data are now easily accessible, and interpretation of the EO data have all contributed immensely to the increased demand for satellite EO data for these kind of studies. So Earth observation data combined with complementary data sets from, say, terrestrial observation and with physical models, or as I said, from crowdsourced data, these have been now widely used for heritage and archaeological studies, revolutionizing the methods of management, monitoring, and documentation. So with the examples that I will present before you, you will see how these have become very, very useful in such studies. So just to do a recap of all the advantages that geospatial technology offers for archaeological studies, the first one being that it can efficiently survey large areas of land and pinpoint the most promising locations for the conventional examination. So because one is able to see it, it gives us a synoptic view, right? And this offers clues that cannot be perceived from the ground. So if you see, if on the ground, when we go and do physical examination, our field of view becomes very limited, and we are not able to see things in relation or context to each other, which forms a very, very important part of archaeological interpretation or heritage management. But Earth observation data offers us a synoptic view and enables us to see large areas of land, and therefore we are also able to see not just the monument or the area that of interest, but also other features in its vicinity and what relationship they may have with the monument. For example, if you look at Taj Mahal, if you take a satellite image of the area and get a vertical view of that place, you will see that it is surrounded by several industries. Now, if you locate those industries in relation to the monument, and if you also add information like wind direction, etc., we will be able to, come up with a plan of how the pollutants from the industry may be, maligning the marble, etc., and what the effect is on the monument. So these kind of studies can be done very easily. The synoptic view of Earth observation data is an advantage in this sense. Advanced remote sensing technologies allow landscapes to be viewed. So the entire landscape can be viewed in light which is invisible to humans. That is, humans are sensitive to seeing only through the visible portion, that is the VIBGYOR, only these wavelengths, 0.4 to 0.7 micrometer wavelength region. Human beings are sensitive only to this region, that is the visible portion of the spectrum. We are not able to see through the other wavelengths, that is the shorter wavelengths like the ultraviolet, or the longer wavelengths like infrared, and even longer ones like microwave. So these wavelength regions also offer very critical information about certain features which the remote sensors are able to give us. Uh, Otherwise, as human beings, through our eyes, we will not be able to perceive this. Therefore, a new light is shed upon these features, and this permits investigators to discover features that are too obscure, maybe under soil or vegetation cover, and they cannot be otherwise detected. So these kind of features will be seen by the infrared sensors or the microwave sensors or the laser sensors. Laser sensors will give us a three-dimensional view. It can penetrate through vegetation cover, so can microwave sensors and so on, and this will give us additional information which otherwise through visible or optical region of the spectrum, through human eyes, we would not have been able to perceive. This is an added advantage. Now, remote sensing can also be used to construct 3D models of the terrain, as I said earlier, through photogrammetric technique, and by taking two images of the same area. Thereby, this allows investigators to search for clues among the topographical features. So if there are mounds, we may investigate that what could be under the mound. Also, the pattern of vegetation or the pattern of soil, how there is an anomaly from the normal, if that can be studied, then what we can do is that the detecting the unknown and seeing the context. So we can look at what is not visible to the apparently visible, and then we can also see the context and do a very enhanced interpretation and go for investigation or examination in detail of the site in question. So, as I said, the natural and cultural heritage is the commonwealth of human beings, and it is very important in understanding of the evolution of the planet and for social development. The protection and conservation of these natural and cultural heritage is our common responsibility. It's the common responsibility of all mankind, and therefore it becomes very, very important. Spatial information technology provides a tool for the protection and utilization of these natural and cultural heritage features. How that it will efficiently and accurately record complex structures remotely. So it is not going to invade into that structure, right? It is non-invasive. Digital information systems are evolving for the presentation, that is visualization, analysis, and archival of heritage documentation. Also, production of multi-purpose ND models, like 3D models. It can be, if I add different dimensions like time, etc., so it becomes an ND model, and these can be used for more than just visualization. So we can use them for visualization and also for higher terms of analysis and archival of the heritage. Now, integration of the 3D model into a 3D GIS for further management and analysis is also enabled through these systems. So potential users here could be, right from planners like the Archaeological Survey of India or the Department of Culture and Tourism, to urban planners, to researchers, students of history and archaeology and so on and so forth, and even common people who wish to analyze the common heritage and that we have. So the overall methodology would be that you acquire data through any of suitable means, or you can even club or complement data from multiple sources. And it is analyzed in a heritage information modeling system, and then 3D GIS analysis can be done to come up with a heritage information system. Okay? So entire reconstructions can be enabled, and the heritage structures can be modeled using these techniques. Now I'll quickly take you through the historical aspect of how this has progressed, the geospatial technology for archaeological applications. So in the early 90s, that is 93 to 95, say roughly, the arrival of the GPS for civilian use made it very useful. We were able to now take precise coordinates and assign coordinates to our mapping work. Then in the second half of the 90s, digital photography was introduced into the global market. And here aerial prospection, simplified the photography process both on board the aircraft and also after flights. So immediate image processing and large-scale digital applicability became possible. Then in the late 90s, the launch of the first high-resolution satellite system for civilian use, that is the IIRS, produced images of very high spatial resolution, both in panchromatic and multispectral domain. This became extremely important for regions where there was a prevalence of small features. For example, wherever there were small pits or small sunken huts at buried prehistoric and early medieval settlements. So this would be earlier when sub-meter level satellite data was not available. The only course left was either fly or an aircraft over it, right? So that was not always possible. So with the launch of this high resolution Earth observation system, these kind of studies became very easily achievable. Then in the mid-2000s, free access via Google Earth to continuous global orthophoto coverage was an advantage that opened up new aspects for researchers. So you could look at high resolution data via a free access portal, and this gave us immense amount of data which could be used for such studies. The next phase from the from 2005 to 2010 approximately, saw the beginning of the application of airborne laser scanning. This was also a watershed marking in the study of archaeological features, etc. Perhaps it was the most revolutionary aspect post the Second World War impact on effective detection and mapping of archaeological landscape heritage, because it is fast, very quick, precise, and it gives us three-dimensional information, and it also gives us digital information. So a three-dimensional digital information which is available to us as very precise and quickly acquired data. So this was very, very useful for archaeological studies as well, apart from being very useful in other application areas. So especially for areas like the heritage site which are covered under vegetation, which could not be studied via optical remote sensing, the aerial laser sensors made this possible. For example, the ancient site of Angkor Wat. So this was hugely vegetation covered and was the aspects of this heritage site were not known. The aerial laser scanning, brought forth all the very buried aspects of the heritage site through the laser scanning sensors. Then the late 2000 onwards, the period saw intensified application of image spectrometry, that is using air and spaceborne sensors, hyperspectral data, and experimentation with automated object detection from remotely sensed imagery. So now advanced data sets like hyperspectral data, and people started experimenting with automated systems like deep learning, machine learning, etc., for automating the classification process or feature extraction of archaeological origin using remotely sensed imagery. Now, the next section we will see how different kinds of data are acquired and how these will be useful to us, in which application areas for in the area of archaeological or heritage studies these can be used. So remote sensing sensors could be space-based, they could be aerial sensors, aircrafts or UAVs, and they could be terrestrial sensors. These continually provide us with data sets with different spatial and spectral characteristics. Then we need to do a series of pre and post-processing techniques for the calibration purpose. Also, big data cloud platforms will allow us to deal with an extensive number of data sets. Please remember that when we use data sets like SAR data or laser data and combine it with images or terrestrial laser scanning data, it becomes huge amount of data, and then big data processing techniques will have to be applied to these data sets. Even crowdsourced data, if it is in huge volumes, then we will need to be using such big data processing techniques. So as you can see, space-bound remote sensing could be active or passive. So it could be through the microwave sensors or the optical sensors or the infrared sensors. We also have airborne remote sensing through platforms such as balloons, aircrafts, or UAVs, and ground remote sensing, like mounting it on certain platforms. We can use laser scanners, terrestrial laser scanners, cameras. In fact, we have done some studies using the cameras on the mobile phones and have been able to generate stereo pairs with those and have of heritage structures as well as urban structures. And we have seen that for certain applications, especially like if you need quick data, near real-time data, and for visualization, these form a very good means of collecting data. And the 3D models that are generated, probably my colleagues will show them to you in the coming lectures, are of a quality which is suitable for such applications. So with this, let us see a few examples of how these data sets can be used for heritage mapping and monitoring. Now, once the corona images were declassified, so these were spy images taken by the United States in the 1960s and 70s and well into the 80s, these have now been declassified. They are high-resolution panchromatic images and also aerial photographs. So the first one is an aerial photograph from 1945. Now, this is the walled city of Beijing. So through historical photographs, people have mapped the area of the ancient walled Beijing old city. So here you will see that there were certain features that have been mapped. Right? The circles indicate the location of the Zizimen Gate. The yellow ellipses show the extension of the avenue, and the pink and blue boxes indicate the landscape transformation. So if we are able to take a look at the features over time, you see that the landscape has changed so much built up area has come up, many changes have happened. But how these features have evolved and how they have left an imprint on the landscape surrounding them, this is the map of through the time series. So in 1945, then in 1967, some changes have happened, and this is 2018. So Google Earth imagery. And this is the map, the layout of the Beijing old city. Then here is an example of utilizing medium resolution panchromatic images. This is satellite data, a study done by Dr. M.B. Rajani and her associates. So you will see this, we will see this through, this is the Nalanda Mahavihar that they have studied, and they have also marked out paleo channels, and here is the heritage area. So the excavated site of Nalanda and the environment, along with the 10-kilometer long paleo channel that drew water from the river Panchana to the site, and this is seen in the Cartosat imagery of 2008. Another very detailed map has been prepared here. So to show you the spread of the identified archaeological remains around Nalanda. And this is a World Heritage Site, UNESCO World Heritage Site. So the core and buffer zones of the site have been also mapped. So you can see this is the core zone and this is the buffer zone. Also the other features like the temple and the monasteries, the water bodies surrounding them, etc., have also been mapped. Right? The green dotted boundary shows us the extent of the entire archaeological site. Then we come to the next very important aspect, that is called spectral archaeology, meaning how we use spectral imaging for archaeological prospection. Now, since buried archaeological remains can change the chemical, physical, and biological properties of the local soil, their presence might be expressed by phenological differences that we see as a manifestation of the spectral reflectance or growth of vegetation. So height of the vegetation may change. So there may be an anomaly that we notice on the surface. So variation in the spectra will be keys to detecting the archaeological marks. So these marks are called soil marks or vegetation marks, right? So in specific cases where the dominant land cover type over archaeological sites is known, then the optimal spectral range can be selected in order to improve the efficiency of archaeological observations using this remotely sensed data. So what I mean to say is that if we are looking at the image and there are some buried structures underneath, say like a wall that is buried or some other feature that is buried inside, the color of the soil on the top may be different from that of the surrounding. So this will be an anomaly that we need to look for and which will be made clear with the help of interpretation techniques. Also, there may be changes in the normal vegetation. So maybe height of the vegetation may be very less or very high. There may be an anomaly with the normal surrounding area. So if we are able to mark these changes, we might be able to pinpoint an area which might give us a clue of something to go for in excavation studies, etc. So with multispectral remote sensing, we capture digital images of the area in different spectral ranges by sensors on board a remotely placed satellite platform. And we call it multispectral because different regions of the spectrum form channels or bands, and each band gives us unique information in that spectral region. Now, these spectral regions can be studied in terms of the percentage reflectance from the feature in particular wavelength bands. Now, if you plot this data, we come up with a signature set called a plot like this, which is called the spectral reflectance curve. And for different features, these are standard curves. Any anomalies that happen can be mapped and can be studied through these spectral reflectance curves. These will give us signatures to study the manifestations of features on the ground, which we see on the image. Right? So as I was telling you about soil marks and clues that these proxies will give us, crop or soil mark. So here you see remote sensing images that are depicting features of buried archaeological remains, most of them through the above mentioned these proxies, spectral, spatial, radiometric, and temporal proxies or clues such as crop or soil marks. So if you see here, there is a buried ditch here and there is a buried wall here. So with these, you see, this is here, there is vigorous growth of vegetation. This is the normal growth, and here there is a stressed growth. So that these two are anomalies, and if we are able to map these and see the reflectance variations here due to the vigorous growth because of the buried ditch and the stressed growth due to the buried wall, we will, these reflectance variations, if they are we are able to pinpoint on the image, then we will be able to get an idea of where to start the excavation work. Right? Then similarly, as you see, this is an enhanced portion. So the buried ditch can be seen and the buried wall can also be seen here. And this is a diagrammatic representation of the electromagnetic spectrum and its behavior as vis-a-vis the anomalies. Similarly, here we see this is another site in the Czech Republic, Central European country, from 2006 to 12 to 15 and then 16. So here it can also be seen on this portal. So crop marks of about 200 pits can be seen here in these images of 4 different dates. Now this is an image from Syria, and here vandalism has been studied. So they have tried to display and detect changes due to looting here. So if you see, this is very high resolution satellite data, and the mapping has been done of areas that have been visibly changed through the time period. Right? These are ground photographs of that area. So there are some pits, small locations here. So here, this was a renewed phase of severe war-related looting, and with fresh pits clearly visible in the same area. So here we can see in the ground photographs also. Now this is WorldView 3 multispectral data. This has allowed the researchers here to discover buried archaeological remains near the Roman port city in Tunisia. So they have worked with different kinds of image processing techniques. Fused data sets have been used. Then PC has been done. Filtering techniques have been also applied. And then certain crop marks, certain orthogonal equations have been applied to get to get information about vegetation, crop mark, and soil mark. And then these have all been clubbed together in decision rule, and this interpretation has been done. These are corroborated by ground photographs of the area. Then another study by Dr. Rajni. So again, here mapping has been done. This shows the extent and direction of floods. This is done through LIS4, study done in 2007. Simulated 3D perspective views have also been shown. So the advantage of photogrammetry can also be seen. Similarly, another similar study. Then hyperspectral remote sensing also forms, as I said, very important part, because it lets us see a continuous spectrum, narrow continuous, and therefore we get very detailed spectral information, high resolution surface spectral information, which becomes very useful for such studies. This is an example of detecting crop marks through airborne hyperspectral remote sensing. This is a study done in Austria, and ultimately the mapping was done for this area. The data processes were implemented in the MATLAB-based toolbox. Then we come to microwave remote sensing. The advantage of microwave remote sensing is that it is time independent, weather independent. So because some areas are persistently cloud covered, and then we will not be able to do any sensing there. This also penetrates vegetation, dry soil, and dry snow. So any heritage structures buried under such features, we will be able to study those. These are also sensitive to soil moisture, vegetation, and snow. And it also has the ability to collect data which are further away from the flight path. So several advantages the microwave data has. So as you can see, optical data, there are clouds. Microwave data, it has penetrated through the clouds, and therefore we get terrain information. Very important for studying, buried features under vegetation or under the soil and so on. So here you see, this is a SAR and GPR based detection over time. So HH and HV polarized images have been used. Okay. So subsurface scattering, this is from the Roman forum at Carantuno. Now here again, spot images have revealed, the radar images have revealed. This is the optical image, and LOS and L-band and SETI P-band images. So these images reveal buried and previously unknown paleo drainage channels, which were afterward also confirmed by field studies. So this is the pulsar-based detection. So ground penetrating radar data can also be validated with this. So in the this is a study area in the Sahara Desert, and all the buried features are very well visible. Similarly, we can also do very detailed GPR-based investigations. Of course, the instrument, it is not very easy to operate it for very large areas. However, for small, when we combine it with the interpretation done through Earth observation data, narrow down to a prospective site, and then use the GPR or terrestrial laser scanner, etc., we will be able to do very detailed mapping of buried structures, as can be seen in the examples here. Right? Then with photogrammetry, we get 3D information. So quickly take you through the concept. We need to image an object from two different locations, right? As we do in everyday life, the eyes image an object twice, and a three-dimensional model is formed. So it could be done from ground-based platforms, UAV platforms, aerial platforms, or space-based platforms. We will show you examples in the coming week, how these techniques have been used, how close-range photogrammetry has been used, how UAV drone-based data has been used, and also from aerial and satellite photogrammetry, how it has been clubbed with the other data sets. So these are the we can get an orthomosaic, digital surface model, contours, and topographic maps of the study area. So here we see a UAV-derived 3D model. Image has been draped over it. These are ground photographs where we see very small structures like artifacts, so pottery fragments, etc. So since it is a UAV image, it will be very high resolution, probably to the tune of centimeters or millimeters, and therefore we are able to see these in the mound. Here these mounds were interpreted, and the area must have been pinpointed. Similarly, this is an example to show you integrated data set management through this is space-based data. This is a study that we did on the Nalanda Mahavihar. So contours have been generated, 3D models have been generated, all the information has been complemented with each other, put into a rule set, and it can be used as a visualization tool. Now here you see 3D models from ground-based technique, laser scanning, and terrestrial laser scan and close range photogrammetry have been done, and these have been incorporated onto the satellite image or on the geoportal. So this can be used for visualization. Similarly, a time series analysis, land use, land cover maps were made for different time periods. Again, the 3D models have been put here. You can also see how the area has changed over time. This is another area in New Delhi, Humayun's tomb, which is also a UNESCO World Heritage Site. So you see a real 3D realistic model which can give you very precise measurements has been generated. This was generated using combined data from terrestrial laser scanning and close range photographs. So these were clubbed together and this detailed 3D model was made. Very detailed descriptions of these will be shown and discussed with you in the coming lectures. Okay, so this is Humayun's tomb, the same in a zoomed out portion. So Cartosat and LIS4 data has been used for visualization. Contours have been generated from this, very high resolution. LULC map of the area, this is where the site is. Yeah. So now you see on the LULC map, the monument, the 3D model, which was generated, has been put. This model was generated using ground-based techniques of laser scanning and photogrammetry, terrestrial photogrammetry. Similarly, another example from the Qutub Minar, the same technique was followed, terrestrial laser scanning and close-range photogrammetry combined to give us very high resolution 3D model of the monument, and measurements can be taken very precisely on this. This is metric data. It has now, we have clubbed satellite data and put it on top of that. The land use, land cover map on the DEM superimposed with the satellite data, contours, very high resolution contours. So these were examples that I wanted to share with you, and this is now for LiDAR remote sensing. Laser techniques are, it is also an active technique. Laser platforms can be ground-based, air-based, or space-borne. So this is the terrestrial laser scanner. We can put a laser scanner on a UAV, can mount it on a vehicle and move. There are space-based platforms as well. Basically, what is happening is that LiDAR is a non-imaging technique. It's a range-based technique. The laser sensor sends laser pulses which strike the object and return to the sensor, to the receiver. And this measurement gives us X, Y, and Z information or vertical profile of the scene. This is also able to penetrate to some extent into water and through vegetation canopies. So this, like the SAR microwave sensors, is also very useful to study features which are buried under vegetation, especially archaeological features. So here you see, this is the kind of 3D model, very dense point cloud is provided. This is a study demonstrating the Mayan architecture, which were buried under forest cover. So you see, this is the forest cover, and through laser scanning, one was able to reconstruct the shape of the structure. Even here, under vegetation, this is the area in optical data in the image. So all of it is covered under vegetation, but through the laser sensor, we are able to see these features under the canopy. Then comes UAV remote sensing. UAV is a platform on which you can mount different kinds of sensors. It could be a hyperspectral sensor, it could be a laser sensor, a microwave sensor, and so on. UAVs are useful because they are lightweight and easy to transport, and they give us high spatial and temporal resolutions. It also provides us quick availability of raw data. Now, there are also some challenges. That is, we have it is limited, by flight time depending on the model or the camera weight and so on and so forth. and it gives us a small footprint data and numerous images. So we end up with a large amount of data. Right? So these are a few examples of the UAV studies that we have done. This is the Bagan Heritage Site in Myanmar. These are two pagodas that we studied. This is the Sulamani Temple Pagoda. These this is a 3D model superimposed on the geoportal, Google Earth, and a very detailed model of the pagoda is seen here through UAV images. Similarly, this is the other pagoda, the Yarhong Gei Pagoda in the Bagan Heritage area. Now you can see the amount of detail. There was an earthquake in 2015 and the pagoda was damaged. This entire heritage site was subjected to great damage. Now you can see the detailed information that is available. All the broken portions can be seen very easily here. This is the 3D model. This is the textured model. On top of the 3D model, the image has also been draped. This data was captured through UAV. So you see, this is the damaged portion and certain study with the here satellite data versus the UAV data was done. What we see here is that satellite data had some areas under shadow, so those could not be studied. But they were damaged. Whereas in the UAV data, those areas, because of the view, a 360 view, those areas can also be studied easily at much higher spatial resolution. So if you see here, these portions were under shadow in the satellite data here. So these are some of the advantages that we have in using UAV data. Now, I have been able to give you, I have been able to give you an overview of all the techniques, the methods of image processing, etc. In the coming lectures, we will focus on each technique one by one, ground-based techniques and how to detect damage and how to document these through laser scanning, photogrammetry, and other such data sets.